Right, so picking up from our conversation this morning, we are now going to talk about the addition of non-acidic electrophiles to alkenes. More specifically, our interest is in the synthesizing of molecules that have multiple functionality. Now, recall that the term functional group in organic chemistry represents anything that is not a hydrogen. Okay? So, as you are seeing here, all the reactions we are studying result in the addition of a substituent that is not hydrogen to the carbon center. And by manipulating the conditions and the reagents, we're able to access a wide range of varied compounds. So here on the screen, what we have is a reaction between an alkene, in this case ethylene, and a halogen in its molecular form. The halogen that's before you is bromine, and you can see that the addition occurs in such a way that one bromine atom is added to one carbon of the alkene, and the other bromine atom is added to the second carbon of the alkene. Compounds that come in this form are referred to as 1,2 dihaloalkanes, and that's because the positioning of the halogens are 1, 2 with respect to each other. So they're synthesized by simply reacting the alkene with the halogen in its molecular form. So if we were to look at the mechanism of this process, it would first start off with our nucleophilic electrons on the alkene attacking the bromine in this case. Now, as it is here, remember we said earlier that the pi electrons in an alkene are actually the workhorses. So they are the ones that are actually initiating the attack on the electrophile. And in this case, our electrophile is the bromine itself. Now, of course, our electrophile contains electrophilic centers. So this being our electrophile, we would now have to identify our electrophilic atom. And of course, we also had said that the reaction mechanisms always proceed in a way whereby there is electrostatic interaction and attraction between the species. So before we actually proceed throughout the mechanism, let's assign some charges. Since we know that the alkene is doing the attacking, we will assign its pi electrons a delta minus, and by virtue of the fact that the bromine molecule is directly positioned above the alkene, it would then mean that there is an automatic induced charge that is equal and opposite. So that means the bromine atom that is nearest to the alkene will carry a delta plus, and that would induce an equal and opposite charge on the bromine atom that is further away. And so you see that there is an alternating series of charges, partial charges, that is being presented here among the species. So this means then that it's possible for us to have two electronegative elements directly next to each other and still undergo nucleophilic attack, or they still undergo nucleophilic attack. And the reason why that's possible is because of electrostatic induction. So here we have our alkene pi electrons attacking the bromine, and the bromine atom that it attacks will be the one that has the delta plus charge, which would then cause the bromine-bromine bond to break, and that would then lead to the departure of the terminal bromine atom, which basically is acting like a leaving group, right? It's going to leave, and it's going to do so with the electrons from the bromine-bromine bond. So these electrons here. So if we are to draw at this point before it leaves, if we are to draw in our electrons, we will see that neutral molecular bromine has three pairs of electrons surrounding each bromine atom. But once the reaction begins to take place, the second bromine atom will leave with the electrons from the BR-BR bond. And so that will show up in the form of it acquiring a formal charge. So let's see how this unfolds. And what we're seeing here is actually that bromine-bromine bond would have been broken, and the bromide now becomes a bromide because it would have acquired that extra pair of electrons. Okay, so at the same time, when the electrons are going back to bromine, or when the bromine electron bonds, what am I saying? At the same time, when the bromine bond is being broken and the bromide acquires electrons, we are seeing that there's a lone pair, or one of the lone pair electrons on this electrophilic bromine here. It actually will attack the alkene. Now, here it says that the bromine electrons attack the remaining alkene carbon. So if we started off, let's track our alkene carbons. The first alkene carbon is the one on the left, which I have numbered 1, and then we have the one on the right. So electrons are moving from between carbons 1 and 2 to attack the bromine, which is what we're seeing here in this first arrow. And then that would have forced our bromine bond to break. But when these electrons moved from between carbon 1 and 2, it created an electron deficiency here at 2, which would cause it to become delta plus or positively charged. Definitely it would become electron deficient. And so in order to compensate or to make up for that electron deficiency, the lone pair electrons on our bromine atom here is going to attack carbon 2 to ensure that this deficiency does not remain. And so that's why we have this, what we are looking at as a closure. So what does that lead to? Essentially what we're getting is a cyclic species that is referred to as a bromonium ion. Now this bromonium ion is our central bromine atom that would have started off with 1, 2, 3, 4, 5, 6 electrons. 2 of them went towards forming a bond here with carbon 2. And so that means that we have 2 remaining, 2 pairs of electrons remaining. And so of course if we check the formal charge of this bromine atom here, what we will find is that it is formally charged +1. So let's do that. Formal charge is equal to group number, and bromine is in group 7, minus the number of bonds, 1, 2, minus the number of electrons in a lone pair, 1, 2, 3, 4. And so that would mean 7 minus 6 is equal to +1. And so that's the reason why the bromine has a formal charge of +1 in this species here. Of course, the bromide that would have left is there hanging around as an anion, and that would then bring charge balance to the intermediate species. And so everything would be neutral. So what we have at this point is a highly strained species in the bromonium ion, right? And so you can see, if you remember from your first year chemistry, you can see that this is not just electrophilic in the sense of the formal charge of +1 being present. It is also highly strained because it is part of a three-membered ring. And we recall from first year chemistry that the smaller the ring becomes, the more strained the molecule will be, because the substituents are forced into a close proximity with respect to each other. So those two characteristics would then lead to this bromonium ion being very unstable and prone to nucleophilic attack. And in this case, since our leaving group happens to also be a good nucleophile, there is a very good impetus for the reaction to occur, for attack to occur. So we can see that our bromide that left a few steps ago is ready and available to pop this ring open, and it does so by way of SN2 ring opening, right? So that's what we are seeing taking place here. Now both of these carbon atoms are equally susceptible, both this one and this one are equally susceptible for attack because they have the same type of, they're not distinguishable in terms of steric strain or anything like that. Both of them are primary carbons. So the displaced bromide does that, attacking, and as a result we have ring opening, and this is how we are able to access our 1,2 dibromide. So essentially our alkene would have gone from being a simple molecule that would have had, in this case, only hydrogen atoms bonded to it, to now a molecule that has the same 2 hydrogen atoms, but now additional functionality that allows it to undergo further reaction. So the presence of these bromine atoms allows for our molecule to become functionalized in such a way where it can undergo further reactivity, either by way of SN1, SN2. Well, in this case, it would be SN2 because these are primary carbon atoms. So our mechanism basically proceeds in a way that is, as we can see, it is a two-step reaction mechanism, but it is also very stereoselective in the sense that we recognize the second step being an SN2 step, and so we know that SN2 reaction mechanisms are always stereoselective. The nucleophile always comes from the opposite side of the leaving group. So our leaving group is there, and it's leaving in that direction, and our nucleophile would approach from the other side, which is what's going on here. And so that results in what we call anti-addition. And so here's an example of bromination occurring in a real context where we have a cyclohexene molecule undergoing the attack or I should say initiating the attack on the bromine molecule itself, where our alkene pi electrons attack the first bromine atom, causing the second one to leave, leading to the formation of our bromonium species, which is then subject to SN2 ring opening. So this is our bromonium. It's a three-membered ring. It becomes opened or attacked by the bromide, which left just a few moments ago, and that leads to inversion of stereochemistry, and that plays out here in our product. Now, I want to give you guys a moment to pay attention to what's going on here. In fact, I'm going to draw your attention to the fact that the bromide, or the bromine atom that was attached first, is pointing above the plane of the board in this case, or the screen. And so the incoming bromide is approaching from the other side, as we expect. But what that would do is it would cause this first bromine atom to remain in position in terms of coming above the plane of the screen. So this bond will break. Let's fix that. This bond breaks, but this bond stays intact. And because this bond is coming above the screen of, because this bond is positioned in such a way where the bromine is above the screen, it means that our bromine will be positioned likewise that way, right? But the incoming bromide that does the attacking does so from the opposite side. And so when it forms its bond with this carbon here, it will do so in such a way that it is going to be pointing behind the screen. And that's what is being demonstrated here. So essentially this is bromine atom 1 and this is bromine atom 2. That's bromine atom 1, bromine atom 2. All right. So we have widened our library and we are now able to build molecular complexity starting from a simple alkene by just shifting around the reactions and the reagents that we are using. On the right, we have hydrohalogenation, which is simply adding a hydrogen, a hydrohalide to an alkene. What that does is it gives us a haloalkane, meaning an alkyl molecule that has one halogen attached. But if we so happen to want a molecule that has more than one, then what we would use is a different set of reagents. And in this case, the reagent would be one that includes two atoms of that halogen. So in this case, we want to add two bromine atoms to our alkene in a 1,2 fashion. So the ideal reagent combination would be molecular bromine in this case. So on to our second set of addition reactions that are non-acidic. I introduce you now to this group called epoxidation. So this is a set of reactions that would allow us to be able to access a group of molecules or a class of molecules that are known as epoxides. Epoxides are highly strained cyclic ethers, and similar to the bromonium that we just saw, we can see why they are strained because, as you are able to witness right now, the functionality is one that includes a three-membered ring that contains an oxygen. And so it's a cyclic three-membered ring, or I should say a three-membered cyclic ether. And so we are going to identify this as our molecule of interest. So the question is, how does one create, or how does one synthesize an epoxide from an alkene? In order to be able to accomplish this, we would have to be able to access a reagent that is able to give us an electrophilic source of oxygen. Remember that addition reactions, the ones that we are giving attention to at this time, are those reactions where the alkene is playing the role of the nucleophile. And so if the alkene is playing that role, let's just put this here. If the alkene is playing that role, then it means that whatever it is interacting with will have to take on the role of the electrophile itself. And so we already expect that our pi electrons will be doing the attacking, and therefore they will be the electron source. And it would therefore mean that our reagent that the alkene comes in contact with will be the electron sink. In this case, that electrophile, or that reagent, comes in the form of a molecule known as MCPBA. And MCPBA stands for metachloroperoxybenzoic acid. So let's break this down. The molecule itself is called peroxybenzoic acid, metachloroperoxybenzoic acid. And so here's the chloro part. And the term meta means that the chlorine is positioned in a way that it is meta to the actual rest of the benzene ring itself. Now, you guys have not been introduced to that notation, and that would not be applicable in this class, so we're not going to spend time on it, but I just wanted to highlight to you where the name came from. So here it is, that this is metachloroperoxybenzoic. So here is the benz part, right? And benzoic suggests carboxylic acid, but because you have two oxygen atoms next to each other, then it would have to be considered peroxy. All right, so if it was just one oxygen, it would have been just benzoic acid, but it's two directly next to each other, so those would be considered a peroxybenzoic acid. All right, so then having looked at that, we are familiar with peroxides, and we know that peroxides are substances that have oxygen atoms directly positioned next to each other. And so similar to the bromine molecule that we just looked at, we are able to see that a peroxide bears the similar kind of feature in the sense that it places two electronegative atoms directly next to each other. And so what that does is it forces one of those electronegative atoms to bear a partial positive charge. Now, that partial positive charge is not fixed. The charge is constantly moving around, and that's because electrons are mobile. So at one point, the delta plus would be on this oxygen, and another point it would shift over to the other one, and back and forth. However, once the actual mechanism begins, or once the reaction begins, whichever the designated delta plus atom is, that's the atom that would be considered electrophilic until the reaction is finished. So, in similar vein, our MCPBA carries the same type of characteristic. Now, our task in this molecule is to, let's just take it in for a moment and observe the different features. So we have a halogen, and then we have a phenyl ring, and then we have a peroxy acid. So these are the three functional groups that are present in this molecule. And the workhorse in the molecule is actually the peroxy acid, because that's where our oxygen atom is going to be coming from. So then, in order for us to identify which atom is our delta plus or our electrophilic atom, it's best for us to start from what we already know. So we know that in a carbonyl, that would be comprised of a carbon-oxygen double bond. And since oxygen is more electronegative than carbon, it's going to carry a delta minus. So you start your partial charges there, and that would mean that the delta plus would go on the carbonyl carbon, which would then induce a delta minus on the neighboring oxygen, and that would force a delta plus on the other oxygen, which is directly next to hydrogen, which is also going to be hesitantly a delta minus for the time being. So let's then talk about, having now assigned charges, we are in a position to proceed with the mechanism. It's not that the rest of the molecule does not matter, but as it pertains to the mechanism, the role players are those that I have assigned the charges to. So that's where we draw our attention. So then, we already talked about that, so we don't need to go into that anymore, but just a little bit more to say with regards to our product. This would be the outcome in terms of the epoxide. So in other words, once the reaction takes place, the alkene is completely gone, and we would have seen that the alkene would have actually formed, it would have actually been comprised of a double bond bonded to two hydrogen atoms and the rest of the carbon ring. Now, once we actually introduce our oxygen to make the epoxide, those hydrogen bonds remain, but we have acquired an additional atom in the form of the oxygen. Now, all carbon atoms remain bonded to four things. So you can see here 1, 2, 3, 4. 1, 2, 3, 4. Right? All right, so that's what has happened to our alkene. And then our starting reagent, which is the MCPBA, would have lost this oxygen. And so it actually becomes transformed into metachlorobenzoic acid. All right, so onto the mechanism. So this is quite a bit to look at, so we'll take it in steps. The first thing that we see happening is attack by the alkene. So we have identified this oxygen as the oxygen that will undergo attack by the alkene. And so the first thing that occurs is attack on that oxygen. And when that happens, what results is this oxygen bond breaks. So the first arrow is the movement of the pi electrons to the delta plus oxygen here. This attack forces the OO bond to break, leading to a movement of the electrons away from it, right? And so that is shown in this arrow here that is designated 2. The electrons move from the OO bond onto the oxygen carbon bond, forming a double bond here. And that would lead to immediate cleavage of the carbon oxygen double bond, which shows up in the form of movement of electrons here in the arrow 3. Now, once these electrons are removed, or once this pi bond breaks, the electrons go towards removal of this hydrogen here. And then the electrons from the OH bond will now close the ring. Because remember, we started off, just like in the bromonium scenario, we started off pulling away electrons from the alkene carbon. And so this carbon here would have become electron deficient. So the electrons have to be resupplied to it in order to address that deficiency. So, ladies and gentlemen, this is a reaction mechanism that is concerted. It's one step, and it means that you have to keep track of the movement of the electrons. So again, we start off with moving the electrons from, if we label them, we'll say carbon 1, carbon 2. The electrons are shared between carbons 1 and 2 initially, and once the attack begins, they are removed. And so arrow A is being used to indicate that removal, and they're removed in such a way that they are attacking delta plus oxygen here. This delta plus oxygen has a weak OO bond that immediately cleaves, and those electrons move from there to the other carbon, and that forces the pi bond here to break, but it moves with its electrons and acts as a base to pick up this hydrogen here. And of course, if we're forming a bond with hydrogen, meaning between this and this, we will have to break this bond. So the electrons from here travel to this carbon here, which is carbon 2. And of course, the result is our epoxide. So here are some examples where MCPBA is being used. In this case, we have a molecule that has 2 alkenes, and this is what we would call a diene because there are 2 alkenes. And so we have MCPBA being used, and the epoxidation occurs, in this case, at the tetrasubstituted alkene. This one is left untouched. And so we are seeing that epoxidation is occurring by the mechanism that we just identified is what we expect. In the second case, we also have another diene, another cyclic diene. And in this case, we do not have MCPBA, but we do have a peroxy acid. And here we are able to observe that epoxidation has occurred because one of the double bonds has been replaced. The reagent here is sodium carbonate, which is the active ingredient in baking powder. It is basic and it is doing the same thing that any base would do, which is to remove a proton. And here we also have sodium acetate, which again provides further basic support. Now, a product in this reaction is actually acetic acid. So we would remove this oxygen here, and the resulting byproduct, I should say, is going to be this guy here. Right? Which is acetic acid, the main ingredient in vinegar. Okay. So let's see what are some applications that can lead us to more diversified compound pool. So we've looked at two ways, well, one way in particular to synthesize epoxides from alkenes, and that used the highlighted reagent MCPBA. But there are alternative ways that would allow us to access epoxides. And those alternative ways include the use of a bromine-water combination. So here we have our bromine molecule. And we have water as a part of the reaction mixture. So when we look at this reaction, we're able to see that in the first case, the bromine is going to do what we expect bromine to do, which is brominate the alkene. And so we can expect that that will take place. Oops, hold on. We expect that that will take place by the mechanism that we expect, that we saw before, in that you have the bromonium species being formed here, the cyclic bromonium species. Once that cyclic bromonium species has formed, we can then expect that our nucleophile will come in and open that up the way the bromide did before, except that our nucleophile is not bromide, it will be water. And that's because water is going to be a better nucleophile than the bromide itself. So if we remember our scale of good nucleophiles, we will recall that the weaker the base, the poorer the nucleophile. Right. So, just 1 second here. Right. So in any case, the bromine will have formed the bromonium ion with the alkene. Water comes in and attacks. And once water attacks, what we have is a double functionalized species that now shows up. Instead of being a 1,2-dibromide, what we have is a hydroxybromide. So in other words, we have a hydroxide on one carbon of the alkene, and then we have a bromine atom on the second carbon of the alkene. All right? We're not going to get too much into the mechanism in terms of SN1 and SN2, but do remember that this reaction does occur by way of nucleophilic ring opening. So if your alkene leads to a highly substituted intermediate, then the mechanism may proceed by way of SN1 or SN2, depending on which one is more appropriate. So here we have the hydroxide having attached itself, and the introduction of base will now cause this hydroxide to become deprotonated. So sodium hydroxide is now being used as a second step in the reaction to afford us this deprotonated hydroxide, which is the alkoxide. And so this alkoxide will now function as an internal nucleophile that will be able to kick out this leaving group here. And it is that process that leads to the formation of our epoxide here. This process is referred to as the bromohydrin method. So we are able to access varying functionality depending on the reagents that we use. And so in this case, you are able to see that epoxides can actually serve as a template, or I should say a launching pad for other molecules to be formed from, right? So we have the epoxide, it is highly strained, similar to the bromonium, and so it's waiting to pop open as long as there's a nucleophile there that is ready to do that. So on the left, what we have is an example of the epoxide being subject to SN2 type nucleophiles. In this case, we have sodium methoxide, where the methoxide represents the strong nucleophile, and it will attack at the least hindered position. So here is our epoxide, and we have two options on where the nucleophile can attack. Now, if the nucleophile attacks here, this is obviously more hindered on the left, carbon here, than it would be on the right. And so a strong nucleophile would much rather attack the right on account of the fact that strong nucleophiles are favored towards SN2 mechanism. So this carbon on the right is actually a secondary carbon, and therefore it is much less hindered, and so the attack occurs here. Methoxide would come from this side and attack on that side of the molecule of the epoxide, and it forces this oxygen carbon bond to break. And that's the reason why your product is such that the methoxide is attached at this position here, while the oxygen is on the left. Now this oxygen is what was originally a part of the epoxide in the molecule in the beginning. On the right hand side, we have what should I say? We have a poorer nucleophile. And so we are therefore able to discern that this would imply the need for an SN1 mechanism. It's showing us that here on the right we have a secondary carbon, on the left we have a tertiary carbon, and that suggests to us that the tertiary carbon would be more likely to be the position of attack for this methanol. Since methanol is a weaker nucleophile, the conditions are acidic, and so essentially what's going to happen is we will protonate this oxygen here, which is our way of activating it into a good leaving group. And once that oxygen is protonated, it is then going to undergo nucleophilic departure. When the methanol, well, first of all, it leaves the way how SN1 mechanism proceeds, and in that process, attack occurs by the nucleophile subsequently. So what are some synthetic examples of these processes? Well, If we take an alkene in a cyclic environment such as cyclopentene and we subject it to MCPBA, we expect that the resulting product would be an epoxide. And so you've gone from one ring to two in that one step. So you've added a ring, and you can stop here, or this ring can be used to further functionalize the molecule by reacting it with a specific nucleophile. In this case, the nucleophile that is being used is dimethylamine, and the attack occurs in an SN2 fashion. And so, of course, if the attack occurs on the left, it would be from the opposite side of the plane that the epoxide is positioned on. So since the epoxide is protruding above the screen or above the plane, then it means that the methylamine will be attacking from the underside. And that's the reason why in the product it is assuming a dashed bond. There are other examples where instead of the epoxide, now we're seeing applications of bromine and bromination in terms of reaction sequences. And so here we have an example of a process that is referred to as bromolactonization. And so we can see that in this initial molecule, we have an alkene that has, it is positioned in a way that is distant from a carboxylic acid. Now, when you look at this molecule, you can expect that there will be some kind of reactivity. But as it currently is by itself, the molecule is not capable of reacting with itself. It's not capable of cyclizing on its own. So this is where functionalizing the molecule becomes useful. Because what happens is when this alkene is brominated, the actual alkene becomes activated, if one can say that. And that activation leads to the formation of a highly reactive intermediate. So bromination would lead to the formation of the bromonium intermediate, which we already have discussed as being highly unstable. And so by it being unstable, it's immediately susceptible to nucleophilic attack by any nucleophile present, weak or strong. So here we have the activation that would have occurred through bromination. Here is our bromonium intermediate. And then we have a sodium bicarbonate base, which we know sodium bicarbonate is baking soda. So this base comes in and is able to remove the hydrogen from our carboxylic acid. Once it does that, it makes our carboxylic acid into a carboxylate, which would then strengthen its nucleophilicity. And here, having had our highly electrophilic bromonium species, we are now in a position where cyclization could occur by way of intramolecular SN2. So here we've done a couple of things. First thing we did was we activated the alkene. And we activated it by converting it into something highly reactive, which was in the form of this bromonium here. And then we also altered the reactivity of our carboxylic acid by actually deprotonating it. Once we remove this proton, the nucleophilicity of our carboxylic acid went up by leaps and bounds, and it would therefore now be a really good nucleophile that could open up this bromonium species that would lead to the corresponding cyclized product. And you know what? At this point here, the reaction has afforded us the cyclized lactone, but there is the possibility for further reactivity because we have this bromine leaving group that is here that would now make this molecule a good electrophile. So any nucleophile that comes in contact with it can do further processing to lead to other compounds. As it is here, there's another example of bromination at work. In this case, there is a reagent referred to as NBS, which we are not discussing at this time. Just know that it is a bromine donor, and it is able to react with alkenes in a similar way that molecular bromine does. And so here we have that being added, and so we have a bromonium species being presented to us as is here. Now at the top we have an alcohol that is part of an ene-ine framework, meaning that there's an alkene group and an alkyne group in the molecule. So this is what you would call an ene-inol, right? And so of course you can see that it's a straight chain molecule. It's linear in its geometry. And that has to do with the fact that we know based on VSEPR that that would be the shape that would be undertaken as a result of the hybridization of these atoms, these carbon atoms here. Anyway, in our bromonium intermediate, again, it is susceptible to nucleophilic attack, and our nucleophile in this case is an OH, which is not so strong, not so great, but again, the heightened electrophilicity of the bromonium allows for that attack to be facile. And so the reaction occurs readily. The three-membered ring pops open. Oxygen is able to attach itself to this carbon, and here we have a product. Now, incidentally, it's interesting to note that the attack is occurring at the more hindered carbon. And so that would suggest that there is some selectivity that is happening here. But for our purposes, we're not giving much attention to that as to why it is occurring. That would be more specific to the conditions under which this reaction was being done. Just know that epoxides and bromides can serve as templates and launch pads for other molecular complexities to be built. So if you recall, when we were talking about E2 reactions, we saw a sequence that I had said to you guys we weren't going to talk about a particular step in the sequence because we hadn't been introduced to it yet. Well, now we have been introduced to it. This is an example. This is the example that we had seen, and it includes a cyclohexene molecule being reacted with bromine to give the 1,2 dibromide in anti-fashion, right? So the bromine, one bromine atom is pointing up, the other bromine atom is pointing back. And then once this molecule has been formed, it is subject to bulky basic conditions. So we have tert butyl oxide. This potassium tert butyl oxide is used to afford us a double elimination. And this elimination is actually E2 in this case because our base is strong and our electrophiles are secondary. So here we have first mechanism, attack occurring on the hydrogen, eliminating the first bromine atom, gives us the first alkene. Second attack occurring on the second hydrogen atom, which is here, eliminating our second bromine, giving us the second alkene. And this is now an E2. This is now a diene. So this molecule is cyclohexadiene. So essentially we've gone from a cyclohexene molecule where we had one alkene present, having functionalized it, basically putting on the two bromine atoms to take them off again, to then now yield us this cyclohexadiene product. And this cyclohexadiene product could then be carried on further in terms of reactivity towards the formation of other compounds such as epoxides and so forth. So here we are, having discussed quite a few reactions today, and your library has pretty much broadened in terms of what it is that you can do with compounds. And so let's go through them one by one. So here we have our generic alkene. And if we start from the left, we would be able to say that brominating would allow us the first compound on the left by way of a bromonium species, which if our bromination reaction conditions include only bromine, then our product would be a 1,2-dibromide in anti-orientation, right? But if our bromination reaction conditions is in the presence of water, which we call bromine water, then we would actually be able to access the 1,2 compound that has bromine as one of the substituents and an OH. Now this can further be diversified if we use an alcohol instead of the water, and that would then afford us an ether. Okay. Second of all, if we take our alkene and we react it with mercury diacetate, again, we did not go through the mechanism, so you can disregard this. Just know that this sequence of reagents would afford us the product. If we take our alkene and we subject it to these conditions where we have mercury diacetate, then we would be able to access the Markovnikov alcohol. So it would mean that our hydrogen would have added at the least substituted carbon. So let's see what that is. We have our alkene here. We have carbon 1 and carbon 2. And it seems that this is a symmetrical alkene. So both, let's see, carbon here, 1 hydroxy. So the hydroxide is being added to this carbon here. Oops. Oh dear. Yeah, our hydroxide here is being added to this carbon here, which means that the hydrogen is being added here. And if that's the case, Markovnikov addition is taking place. This would be the same product that you would get if you were using a regular acid and water. So this is just to show you that there are multiple ways to access alcohols from alkenes, and those ways are chosen according to the targets and the objectives of that synthesis in terms of what will react with what and how to minimize those side reactions. So moving on, we have here the same alkene can be subject to epoxidation conditions. So if we subject it to MCPBA, then we expect an epoxide to form. And that epoxide can be reacted with an amine, and there we are able to get amino alcohols, which is not too far away from amino acids, which you will find out about in the next week. And then here If we take our epoxide and instead react it with an alkoxy nucleophile, we are able to get ether alcohols in this 1,2 orientation. So as you're seeing, the variety of options that become available increase as we are able to increase our reaction pool and our reagent pool. Finally, hydrohalides can be applied to the alkene, and if that's the case, we are able to get an intermediate carbocation, which is then subject to nucleophilic attack that will occur in Markovnikov fashion. All right, guys, so I think this is a good place to stop. It is 25 minutes past the hour. We're not going to take up the whole time. We'll take the time now to ask, to answer your questions and to work a couple problems to see that this stuff is actually cemented as we proceed further. So I am going to stop the recording at this time, and I will put on the screen, I'm going to put on the screen